Okay, we'll get started. Today we're going to talk about the different types of PVT laboratory tests that are conducted. This is discussed in Chapter 6 of the book, and then we probably won't get to it today, but the special the tests that are conducted on oil samples are also discussed in some detail in Appendix D. That's for oils. And just to give a summary of the types of tests that laboratories do on fluid samples, we talked yesterday about compositional analysis and sampling. We talked about bottom hole samples and separator recombined samples. And in connection with both types of samples, one also measures the molecular weight of the flashed stock tank oil, so to speak, in both the separator oil flash and in all of the bottom hole type samples flash. And this molecular weight of that overall oil, flashed oil, was used to calculate or back calculate the molecular weight of the very heaviest fraction, C10 plus, C15 plus, C35 plus, whatever it is. And it's an important piece of data that's used in converting the mass fractions measured by the laboratory to mole fractions. So it is part of the compositional analysis, these molecular weights. So I'll include that as well. So basically we have gas chromatography is the main instrument used, and what we're really measuring here are mass fractions or weight fractions, and then those are converted to mole fractions. Such analyses are conducted, all of these, both on oil samples and gas condensate samples, the bottom hole as well as the separator recombined. So all types of reservoir fluids will be analyzed chromatographically, more or less in the same way. These are laboratory tests. These are measurements just like density and other types of data we'll be talking about today and next week. It's just that these measurements are of a compositional nature. So, any questions about this? So this is the first type of analysis. Now, we talked about PVT data needed for engineering calculations being what? We need to know how many phases we have. Okay? So we need to know whether it's one phase or two phase. And the condition that determines that is the saturation pressure. Right? So that we need to know what is the saturation pressure above which it's single phase and below which it's two phase. And if it's two phases, we also need to know the amounts of the two phases. And then either single phase or two phase, we need to know the properties of density and viscosity for each phase. That may also involve knowing the composition of the various phases. So just to remind ourselves the type of data needed, just as a before we go on to list the different experiments. So basically the data, the PVT data needed includes phases, the number of phases, which basically is saturation pressure. Whether it's a bubble point or a dew point tells us whether the single phase is considered a gas or an oil. And if you're below the saturation pressure, then you have 2 phases. So the number of phases, the amount of each phase. And when we're talking about amounts, we're talking about in terms of mass, maybe volume, and sometimes perhaps the moles of each phase. These would be different expressions for the amount of each phase. And then we need to know for each phase the phase properties, what I'll call, and those fall into basically 3 categories. The one is knowing the density. It's typically the mass density, the kilograms per cubic meter. The viscosity used in all transport modeling, and then potentially the compositions of each phase. Now, the composition of the phases may be needed to help predict or correlate the properties, density, and viscosity. That may be one reason that we want to know the compositions. But more often, when we measure the compositions of these phases, we're interested in the design of surface processes. Remember how much more money we make by getting these C3, 4, 5, and 6 components to be sold as part of the liquid, the stock tank oil, versus being sold as part of the gas. And we'd like to know, how does the distribution of these components, see-through and heavier, change for the various phases? And so that that's kind of a second reason for needing to know the compositions, would be for surface process design, engineering, calculation. Okay? And we typically need these data as a function of pressure at reservoir temperature. That's for reservoir engineering applications. But you also need some of these data at a wider range of pressure at temperatures from reservoir down towards standard conditions. This would be for 2 purposes. Where do we have these kinds of pressure temperature conditions? We have it in the surface process separators, and we have in the production tubing, the tubulars that bring the reservoir fluids to the surface, so in pipe flow. So this is kind of the space, the pressure temperature space that we're interested in. But we talked yesterday about the fact that we may have compositional variation within the reservoir. We may have a gas cap on top of an oil, okay? And so you might have a very wide range of producing compositions, not just the sample composition that you collect, but you may expect that the composition being produced as a function of time can change considerably. So we actually have another dimension in this PVT space, which is composition. I'll just write it up here for various compositions. So we call this a pressure temperature X for composition, or Z space. And so we might collect 3 samples, 1 in the gas cap, 2 in the oil, and if we do the PVT analysis that gives us pressure temperature dependence for each of those 3 samples, in effect what we've done is that we've calculated a large pressure temperature composition space with measurements. The composition space being gas cap sample, a high up oil sample and a low down oil sample. Okay, so you normally capture this variation of PVT properties in terms of composition by doing a complete set of PVT experiments for several different fluids that have collected from either the same well or various wells in the field. Okay? That's at least in the traditional sense of the word. So basically when we want this pressure, temperature, composition space covered, this is by doing the set of experiments that we're going to talk about for multiple samples that have been collected. Okay? Where each sample will provide, in a sense, the pressure temperature dependent properties of where the phases are 1 and 2 phases, the amounts of the phases, and the properties of the phases. So is this clear? That's kind of the game plan. And now what we're going to talk about is for a given sample, making a set of experiments to help provide this information. So each experiment I'm going to try to say, well, this is the way the experiment's conducted, kind of the mechanical, so that you understand how the laboratory is doing what it's doing. But then we're going to talk about what measurements are made, okay? And sometimes those measurements are directly reported, and sometimes they're transformed into quantities that you'll find more easy to work with. So they don't report necessarily the measured data themselves, but they transform them into other properties. So we're going to look at basically for each test, so for each PVT test, we're going to look at the procedure, the laboratory procedure used, and the second is the data measured, and the third is the data that are reported. Like I said, sometimes these are the same and sometimes not. Okay. What I'm going to do here is give myself some more writing space. Put that down here. And then I'll just continue on listing the different types of tests here. Okay? Whoa. So the first test that we're going to talk about is usually referred to as the constant composition experiment or expansion. I'll just write EXP, whatever you like. We usually abbreviate it CCE. Sometimes it's called constant mass expansion. Some of the laboratories will use that terminology. You basically take your sample, fill the PVT cell, which is some kind of a steel container. It might have windows that you can visually see what's inside, sometimes not. And this container, this PVT cell, is filled with your reservoir fluid. And then you basically do all the measurements without taking anything else out. That's why constant composition or constant mass. You charge it once, you're done, you do a bunch of experiments. Okay? So that's the reason why we call it the constant composition experiment. This is conducted both on oils and gas condensates. And the primary data that it's providing us is the saturation pressure, whether it's a bubble point or a dew point. So the saturation pressure type. And basically it'll give you densities at pressures greater than and equal to the saturation pressure. It will always give you this information. Okay, so at this saturation pressure will be at the reservoir temperature. In fact, all of these will be typically at the reservoir temperature. I'm going to draw this a little bit different. You may, in a seldom situation, ask for the same experiment at lower temperatures also. Maybe 100 degrees Fahrenheit, 30 degrees C, something like that. But it's not so common. But you may also ask for at temperatures less than the reservoir temperature. The other kind of data that it may provide to you is the phase amounts below the saturation pressure. So basically the gas volumes as a function of pressure less than the saturation pressure. So it'll give you these gas and oil volumes at pressures below where there are two phases. And since it's not always measured, I'll just kind of put it in purple. It's sometimes. Now, it will always be measured, this two-phase here for gas condensates. This will always be measured for both oils and gas condensates. But the two-phase phase behavior will always be measured if it's a gas condensate. Sometimes it'll be measured if it's an oil. Okay? So the stuff that sometimes I'll try to put in purple. Okay, so that's okay. Then we've got what we call a multi-stage separator test. A multi-stage separator test. Which I'll just abbreviate SEP to have some kind of shorthand. And in essence, it takes our reservoir fluid and it subjects it to a multi-stage process like this. We've talked about it before, where it goes through. Typically it'll be 3 stages, maybe 4, taking gas off of each stage and ending up with a final stock tank oil. This almost always will be conducted on oils, practically for all systems, all oil systems. for some oils, at least in the older reports, they don't do it so much anymore, but in the older days, they might do 2 or 3 or 4 of these for the same oil. And the reason they're doing that is to try to help identify what's the best set of conditions, particularly right here, pressure usually, maybe temperature, that gives the most stock tank oil. So it's trying to help in that optimization of the surface process. Now, it's not so common anymore to do this because we have Excel, we can do it in a classroom exercise, and we can actually optimize or design the separator pressure temperature of the first stage using calculations instead of doing it experimentally. But this will always be done for oils. It'll typically be either a 2, sometimes as many as 4 stages of separation. Gas condensates, depending on how much condensate is coming out of the gas, okay? It may or may not be used for gas condensates. I'll put that in purple, and I'll kind of make the footnote that for gas condensates, it needs to be what I'll refer to as a medium rich. It's like going to a damn class in Spanish or some foreign language you don't know. There's so many new terms that you're learning in the course. I don't do it to confuse you, but these are terms that are going to keep coming at you later courses. A medium rich gas condensate. You have rich condensates and lean condensates. These are concepts. Lean condensate is one that doesn't give you a lot of added value, the condensate. Maybe less than 25% of the daily revenues comes from the condensate. Maybe less than 15%. Okay, it's lean in terms of money. Okay, so it might be, well, I'm not going to tell you the numbers, but it's basically, you're getting some revenue from the condensate that comes out here, but most of the revenue is still coming from the gas. A rich condensate, the majority of the revenue is coming from the condensate, and you're getting only some from the gas. That would be a rich condensate. It means you're getting rich off the condensate. A medium rich condensate is somewhere in between. Okay? So that's kind of the deal. So what it really means is that the ratio of oil to gas, the volume of this oil here, this condensate, to the total amount of gas here, okay, this oil here. So basically, if the volume of this oil here to the volume of this gas here is approximately greater than, you have to give me to convert, about because I have to think upside down here. I'll do it in my barrels first, and then I'll give you in the, okay, greater than about 100 stock tank barrels per million standard cubic feet, which is the same as, let's see, if I've got 100 barrels per million, that means I've got a 10,000 GOR, which you divide by 5. It gives you 2,000 cubic meters. Inverse of cubic is 500. So you have to multiply by 5. So that's about 560, I think, standard cubic meters of condensate per million standard cubic meter of gas. I think that's right. It's Friday afternoon, so I'm going to give myself the, okay. Because if it gets much leaner than that, then the laboratory, in other words, in the laboratory, the physical volume that's being created in this little experimental separator apparatus is on the order of a few cc's. And if they get some experimental error with 1 cc and it throws off completely the ratio, that's not a good sign. So it has to do with the physical amount of condensate that's being created in the laboratory test. It just becomes so small. So if it's less than certainly 50 barrels per million standard cubic feet, it's hard to conduct an experiment that yields enough physical, measurable amount of stock tank condensate. So that's okay. So that's the second kind of test. And I think if we're lucky, we'll get through these two tests today, the second hour. Okay. And then we have what's referred to as depletion tests, which are conducted at reservoir temperature. And they're intended to give properties at reservoir temperature. Basically, the amount of the phases that form and the properties of those phases as a function of pressure. So basically, it's trying to give you gas and oil volume as a function of pressure, basically below the saturation pressure in some form or another. That's what it's trying to give you. It's trying to give you the densities of the gas and oil phase as a function of the pressure, and it may give you gas viscosity and oil viscosity. That's not always the case, so I'll put that kind of in over here in purple. So basically, these properties, the amounts of the properties and the amounts of the phases and the property phases are for pressures less than the saturation pressure where it's two-phase. And this kind of experiment is conducted, of course, both for oils and gas condensates, but there's two types. The one is, we're not going to get to them today, so we'll talk about them next week. I'll just list them. The one is referred to as a differential liberation. DL. And the other is referred to as a constant volume depletion. CVD. Okay. And this differential liberation is only measured on oils and basically is never measured on gas condensates. There's always the exception to the rule, but it's not recommended, and it almost never is conducted, a differential liberation on gas condensates. I've seen it done once. Well, twice by the same laboratory for the same field, but it doesn't mean it hasn't been done more than twice, but I've never seen it, and I've seen a lot of these reports. So it's very unusual. So I'm just basically going to say not recommended, not done. For the constant volume depletion test, this is always what we conduct on these gas condensates, and it may be conducted on certain types of oils. Oils that have a very high gas-oil ratio. But it's something we'll come back to. It's called near critical oils, or it's unusual, but it can be used. So this is giving us the entire suite of conventional laboratory tests that will be made. So the first one is the constant composition expansion. It's primarily trying to give us information about what pressure do we start seeing two phases, okay? What are the densities of the single phase mixture, and possibly it may give us some indication of the amount of phases below the saturation pressure. That's the one test. The multi-phase separator test is mainly conducted to get information to help design and optimize the surface process. Okay? We're trying to make 20 times as much value from components, keeping them in the stock tank oil phase instead of letting them get released into the surface gas phase. So we're doing these experiments mainly to do what I refer to as, this is my little box for surface process. That's the surface process. And we're basically trying to do some kind of optimization on this. And these data help us do that. And then we've got the depletion tests that are giving us these phase volumes that we need below the saturation pressure, the phase properties of density and viscosity. And that's it. Now there may be some compositions as well that come out here. I'm going to put that like this. But again, it's not always done, but I'll put it in purple because sometimes they do measure these equilibrium compositions. Okay? That's it. I mean, those are the suite of tests. So chapter 6 beats with a hammer all of these experiments. I mean, that's all it's doing. Okay. And that chapter will put you to sleep, almost guaranteed. If it doesn't, if it stimulates you, there's probably a company you should look to go to work for here in Norway. It's a laboratory company. There's several of them, but you know, if you get excited about chapter 6, something's wrong with you first. I mean, no, I shouldn't say that because it's interesting because I work with a lot of data from these laboratories. And so generally I see the quality of the data being directly correlated to the boss of the laboratory, the manager. And it's very interesting because if the manager is one of these crazies who loves this kind of stuff, and that guy or that girl, though I haven't, actually I know there's one lady manager, PVT laboratory in Houston. So that manager will whip the butts of all those people working under it to make sure that they do good work. And if the manager would rather be out drinking with the president of Schlumberger or somebody like that, or don't care who they're drinking with, and don't really care about, okay, then the quality of the laboratory data will be proportional. So whenever I'm looking for a laboratory, and if I know the person's still there, still running the laboratory, seeing good data from them, talk to them, discuss with them, that's a good sign. So there are a few of these crazy people out there who really enjoy doing Chapter 6 stuff. And if you find one, become good friends with them. Okay? So that's kind of the, that's basically, and then this Appendix D, what Appendix D does is that it basically takes, for the oils, and it hammers to death the oil tests, the differential liberation and the multi-stage separator test. And it's hammered to death. It's directly a report that I lifted from Standing, who you guys know about, who wrote this as part of his teaching curriculum and used it in the book as Appendix D. So and he was a very good communicator, and so hopefully Appendix D will help you understand those experiments better than Chapter 6. See if I've forgotten anything here. You need to realize that every measurement made and every data provided in a laboratory report has uncertainty. Nobody measures perfect data. They don't measure perfect compositions of the samples that are collected. They don't measure perfect saturation pressures. They don't measure perfect densities. There's an uncertainty associated with every piece of data. So you need to keep that in mind for various reasons. But in general, most of these data, in general, should be measured within an accuracy of about better than 5%. The important data should be measured within an accuracy of 3%. In general, they are. There are a few data that are important and are still not reliably measured in laboratories. But in general, that's what we can say about it, is that all of these data have uncertainty associated with them. Why? Well, you know, I mean, the people working in the laboratory also go out and party and have family problems at home, and I mean, everybody makes mistakes, right? The equipment is not perfect equipment. It's not always calibrated as it should be. It's just like everything else. That's why, you know, even doctors and everybody makes mistakes occasionally. Sometimes it has serious consequences. But anybody who says they've got perfect PVT data, then they're not drinking, they're on drugs. Okay, so we'll get started here with the first test, which is this constant composition expansion test. And we'll be able to talk a little bit about it before the break. As already mentioned, its main purpose is to get the saturation pressure, certainly at the reservoir temperature, maybe at some additional temperature as well, but you know, certainly this one. And to get the densities at reservoir temperature and for pressures that are greater than that saturation pressure. Those are the data, the main data we're getting. There's basically two types of tests, two types of equipment, and two types of tests that are used to get this information. The one is for oils only, and it's for generally what we call lower to medium gas-oil ratio oils. And I have to tell you what those numbers are. Typically that would be anything with a gas-oil ratio less than about somewhere between 1,000 and probably 1,500. You can use this reliably. Standard cubic feet per stock tank barrel, and that would correspond to about short of 200 to 300 standard cubic meters per standard cubic meter, something like that. And what it's doing is that it's doing it as a very, very simple experiment. You can't almost go wrong with the experiment. And they just simply monitor the cell volume. It's a blind cell, so they don't have to see anything inside it. So it's a blind cell. And they start out here, and basically at pressures where it's single-phase oil, the volume doesn't increase very much as you lower the pressure because it's just slightly compressible. Okay? So it's got a slight slope to it going down. And if it stayed single phase oil, it would keep looking like that. But what happens is that you get some gas coming out of solution, and this total volume kind of shoots off because you get a little bit of gas coming out of solution. That gas has got a much higher compressibility, so the system compressibility is discontinuous. Okay? I'm just going to sketch the system compressibility. You guys know what that is, right? It's basically 1 over the volume, the change in volume over the change in pressure. So this thing is basically it's low value down here, and then it just jumps up like this. So there's this discontinuity right here. And you basically can plot the two trends, and where those two trends intersect is pointing to the bubble point pressure. Remember, it's going to be a bubble point because we're only using it for oils. So this discontinuity in the pressure-volume relationship caused by this discontinuity in the compressibility between single phase and two phase. And of course, you know how much mass that you charged into the cell. Okay, the total amount of mass that you charged into the cell. And here we have the volumes of the cell as a function of pressure above the bubble point, right? And density is very simply calculated as the mass, which does not change, constant mass, divided by this changing cell volume. That's a function of pressure, and that's a function of pressure. So this is how the lab comes up with the table of densities. So they measure the volume and they calculate the density, knowing that the mass is constant and fixed. There may be a piece of equipment they connect and measure density directly. That some labs have that, but generally speaking, they do it by this method. How does what? The equipment? That I know we can find. I'm sure. You've got a problem. If you're interested in what the equipment looks like, he may be one of those animals that we want to get in charge of a PVT lab. Okay, Ruska blind PVT cell. There's some old guys. Let's see if we can find a modern version. You know, I actually did this kind of experiment. That doesn't look good. Blind PVT cell. Well, this doesn't look like it either. This is kind of a sketch. That's too bad. Ruska, let's just look at PVT cell. I don't know. You know, the cell is usually immersed in an oil bath to get the temperature right. And so there's not so many pictures. It's usually immersed in this oil. So if we, maybe if you remind me, you can take me downstairs. Probably they still have some of the old ones from the 70s. Now we're getting into some pretty risque stuff here. So, yeah, it's a piece of steel, and it's got, I don't know, it's piece of steel with a hole inside of it. That's the cell. Okay. We've got some acrylic here, right? Is this, huh?
Sure.
There we go. Russian. Okay, so that's it. We take a break now and come back and talk a little more about this for